Alright, welcome back. So, how good can a quickly trained multitask model perform? Well, in this video, we can find out. So, in the previous video, we went over the training process for a multitask model. So, what that process was, we initially do most of our training at a quarter resolution to quickly get a good model, or we'll say efficiently get a good model, because that took a long time, about 20 hours to train for 150 epochs, and we still had more room for improvement. In the next two training sessions, we fine tuned at a half resolution and fine tuned again at full resolution. And there's minimal hyperparameter tuning, and honestly, I would say minimum augmentations. We could have used another library like Albumentations to do some very intense augmentations to improve the performance of the model. But right here in this notebook, I just want to show some examples of inference. And so in this right here, we have a validation sample of a scene with a lot of pedestrians in the background. You really can't see them here, and you could really see them more so in the segmentation. They're labeled by this red, and we have some cars, some traffic signs, and you can see the depth map. It basically picks up most of the pedestrians. But I want to note this light pole right here to the left. So this light pole right here. So in this prediction, you can see that the segmentation is kind of jacked up. It doesn't get all the street signs. It gets some of the pedestrians. It doesn't label them out. It just says, here's a blob of pedestrians, here's a blob of pedestrians, here's some other blobs of pedestrians. And really messes this thing up right here and doesn't really get the street quite right. Thinks there's signs on the grass, and that's not the case, but it segments half a pole. And you'll notice right here in this depth map, so you can see the cars, you could even see some of the pedestrians in the background, cars. You see the full pole, but in this case, we really have. It says that half this pole is significantly closer than the top half. So the bottom half is significantly closer than the top half. So you might have realized by now, in a depth estimation, we'll look at the original image on the left. You could see that if we go down for this bottom square, all this stuff right here is relatively closer, and that is a bias from this data, from this depth data. This whole thing right here is going to be much more closer than this top rectangle right here. And the data preparation, we somewhat prepared for it with this depth normalization by normalizing our depth to have more well-behaved distribution besides this super spiky, super biased distribution. But it still kind of shows up in this thing right here. So you can see in this depth image, there's a little, you can see the horizon. So it seems like it learns the horizon, but it kind of is similar to the truth data, but it also, there's a pretty big difference between this depth information and this top depth information. And that's apparent in the truth data, but it seemed to override the fact that this pole's right here and it shouldn't, be further back. But what's really interesting about this is the half segmentation. So since we're jointly optimizing this and training this under a joint optimization, we can see that it's possible that this depth bias leaked into the segmentation training and influenced the way that the segmentation works. So that's something to really consider when you're thinking about what's driving predictions when you're training these types of models, and to see what kind of, how the data from one task can impact the performance of another task and vice versa. And here's a clear example, a clear failure of what could happen when you don't account for certain biases in your data. So let's actually look more into the depth data. So what we're going to do is right here, we have a random sample. We're going to sample 94 predicted depth maps and true depth maps and save them. And we're going to plot their distributions right here. So here's the true distribution. And remember, we clipped it to 250. So if you see right here in our depth normalization, we actually clipped everything to 250, and then we normalized it, and we still have that clipping artifact right here at the very top of the distribution. And you can see right here, we essentially unnormalized the distribution back to the original from 0 to 250, and we still have this artifact. And then here's the predicted one. So you can see how this is rough and is has different distinct places right here, here, and this is smooth. Well, this true depth distribution is rough because the depth of different objects, this light pole right here, this is all going to have roughly the same value. These cars are going to have roughly the same value. The sign will have roughly the same value. Everything, all these dense objects are going to have roughly the same value, which is kind of why you make it similar to segmentation. So if we could use this kind of knowledge right here and apply this to our depth loss function, we might be able to increase the performance of the depth. That'll be for a different time. Another interesting thing to note is that it seems like the model learns two distributions. It seems like it learns this, this one with this huge spike up here and, goes down like that. And it looks like this is a background distribution and that this might be a foreground distribution of objects. So if we go to the snipping tool, I'm just going to draw on this right here. So take the red pen, and it looks like we have something like this. And then it looks like this background, it could be like this. So it looks like we have a mixture of distributions. And that is another important thing to think about when you're, seeing what's driving predictions. What distribution is your model learning? So that's another thing to investigate. So I think that's all for this video. I just wanted to show you an overview. Oh, let's go look at some other predictions. So let's do a random one. Let's do test data set 503. You can see right here it thinks everything is forest, but we still get the cars, the road, the motorcycle. It gets some nice detail. And, this is pretty, overly smooth is generally what I've noticed with these depth estimations. Let's try one more. Let's try 53. Oh, that's not what I just did. Oh, let's try it. Alright, so right here is not bad. See, it seems like there's a failure mode with this dark area on the corner. It can't really tell if that's a sidewalk or not or what that is, but it gets the cars, gets the trees, gets the sky, and the depth performance is pretty good. We get these close-up cars right here, and you can see it does get these further away cars. So that's all for this one. I hope y'all learned some stuff about multitask networks. Hope you learned about what to look for during the training of these models and how to think about what's driving predictions. That's one of the more important things when it comes to actually deploying your models. You really want to know what is making the prediction. So I'll see you on the next one.